let's get this started. Thank you everyone for coming. Just first to start, some procedural notes. Orion, well, welcome to Orion's PhD Defense. And Orion will present for about 45 to 50 minutes, after which we will have an open session for questions from anyone in the audience, including the committee. And right after that, if the faculty in the room want to do it, we can have a closed session of questions with Orion. After that, we'll have just the committee a discussion. And after that, we'll invite everyone back to the room so that we can sort of tell Orion the deliberations from the committee. What's that? Well, we will tell him the deliberations in any case, right? If he passes, then we'll celebrate. So thanks, special thanks to the committee for being here. Have Kevin Lynch joining all the way from Northwestern University. Hi, Kevin. And say hi if you can hear us.
I hear you fine, thanks.
Awesome. Tranjafilos Aquilas, thanks for being here. And Neville Hogan, thanks for being here. Also, special thanks for Orion's family for being here and giving support in this very special day. I know that it's special for him, but it's special for many of us. It's indeed very special, right? I remember back in the day, Orion, all the way from his the words in his research statement. For some reason, I don't know, this is very uncommon, right? Like as faculty, you might read over years like hundreds of research statements, but for some reason, sort of the authenticity and the commitment of the words in his statement sort of stuck in my head. I remember he finished his statement with like, "I am ready," literally. Those were the last few words in his statement. And I would say that sort of those two things, the authenticity and the commitment, sort of have characterized Orion through these years. Orion is a person who he knows who he is and what he likes, and he doesn't pretend otherwise, and that's sort of kind of refreshing in our environment. Orion is also very committed to do and to solve research problems once he knows that he's ready for them. And that's also very, very refreshing, right? That he doesn't need like external validation or external motivation. He sort of chooses his own problems and sort of why he's interested in them. It's great to work with someone with those characteristics. Today, Orion will present on sort of the last piece of his PhD on this sort of kind of maybe esoteric topic of contact configuration regulation, which hopefully he will explain us why this is important and essential component of a manipulation system. But sort of the same authenticity and commitment he's shown several other times through his time here, all the way from sort of the beginning of his PhD, working on the connection between shape and motion and how those are important when thinking about end effectors or grippers in general or interaction. But as a key member of the Amazon Robotics Challenge for 3 years, extremely important through that journey. What I would say maybe even more shows even more in sort of his incredible commitment to teaching at MIT. He has, as he was saying before, has participated in teaching dynamics and mechanical engineering for many, many semesters, and has made many students happy and a few faculty also very happy that we had someone like him supporting us in teaching. And it shows like when Orion sort of puts his mind into something, he just goes for it. And he just sort of enjoys the truth that is in teaching something as pure as dynamics, just like a good match for him. So Orion, I don't know about you, but I'm super excited. So thanks for being here. The stage is yours.
Thank you. Is this on? Hello? Cool. This meeting is being recorded by host or participant. Got it. Thank you for the great introduction, Alberto. Welcome, everyone. Welcome to my thesis defense My name is Orion, as you hopefully know. And today I'll be presenting the culmination of the research that I did at the Manipulation and Mechanisms Lab at MIT. The title of this work is Manipulation of Unknown Objects via Contact Configuration Regulation. Quite a mouthful. What does it even mean? So essentially, I designed a robotic estimation and control system that could reactively manipulate objects that it had not seen before. Robots. They're everywhere. They're very, very cool, and they're coming to get you. We've seen huge advances in robotics and artificial intelligence over the past few decades. They can make cars, they can deliver your groceries, and they can beat you at board games. That being said, robotic manipulation is a very difficult problem. Deep Blue beat Kasparov back when I was like 5, and yet even today, a toddler could move an actual chess piece on a board better than a robot. There's a term for this, it's called Moravec's paradox. So why is this the case? There are many reasons, and for a thorough analysis, I would point you to Matt Mason's survey paper towards robotic manipulation, but I'm going to focus on 2 of these in particular, contact mechanics and uncertainty. So let's start with contact mechanics. Contact mechanics results in systems with multiple modes of interaction. So are you in contact or not in contact? Is your contact sticking or slipping? How many contact points are there? So each of these interaction modes has its own set of kinematics and dynamics. So this leads to 2 issues. First, transitioning between 2 types of contact interactions leads to discontinuities, which is very challenging for estimation and control. So think about impact, right? So if a ball bounces against the ground, right, at that instant, we often treat it as if just the velocity just flips from one direction to another. And so for many of these continuous algorithms, like gradient descent or Newton's method, any sort of discontinuity really throws a spanner in the works. So the second issue is hybridness. So having multiple interaction modes leads to sort of the combination of discrete and continuous behavior. So we call that hybridness. So for instance, if you're manipulating an object, the pose of the object, so its position and orientation, are like continuous variables, but whether or not it's in contact with something else and how many contacts there are, those are all discrete variables. So the juxtaposition of discrete and continuous elements adds a combinatorial aspect to many of the planning, control, and estimation problems that you have to deal with in robotics. And that just increases the combinatorial complexity like a lot. So that adds an extra challenge. So on the side of uncertainty, uncertainty brings its own challenge. In a manipulation system, ideally, you shouldn't have to know the object beforehand. You don't want to be tailoring your system to the specific object you're manipulating. But that means that your system needs to be very underspecified, and it needs to be robust to a variety of object shapes and sizes. Then also, you have an estimator, but your estimation can never be perfect. So if your robot is like opening a door, you don't want it to rip the door off the frame just because it didn't perfectly predict the motion that the hand needs to go to rotate the handle and open the door. So you need some degree of compliance to allow for estimation error, so things don't just break. So with this in mind, let's take a look at this video of my lab mate Sang-Woon and I working together to move a box around. Look at us go. Let's make robots that can do this. Oh, what's going on here? Cool. But what is this exactly? I'd like to point out a few capabilities that we are demonstrating. Are things working on the Zoom? Yeah. Cool. So first, we are able to regulate contact behavior. So I'm able to keep my palm flat against the box, and I'm able to apply a force in such a way that it keeps my hand from sliding. Second, we are regulating the box's pose. We're moving it up and down, side to side, rotating it. Third, the system is compliant. So if I push the box, Sang-Woon doesn't just topple over, right? His hand moves in response to that. And then finally, we are relying on a combination of visual and tactile feedback to stabilize the motion of the box. So we'd like to make robots more dexterous. I've outlined some of the challenges of manipulation and some of the human capabilities that we'd like to see in robots. So using this, we can write down some design goals, specific ways that we can make robots better at manipulation. As I list them out, I'm going to show some demos of the robotic system that I created accomplishing these goals. So let's start with compliant motions. The robot should not fight against the kinematic constraints of the system. So here in these videos, the robot is trying to keep the object at a constant angle, as well as regulating sticking contact at both the hand and the ground. At the same time, I'm moving the platform under the object in a circular motion. So the robot doesn't fight against me interrupting the system by moving the platform. It just focuses on its regulation objective. We want our system to be robust to a variety of object shapes and sizes that aren't necessarily known beforehand. So here, the robot is executing the same sequence of operations on 4 different objects. So as I mentioned before, hybridness, the combination of continuous and discrete behavior, presents a challenge for estimation and control. However, it is also an opportunity. It is possible to sequence different interaction modes to drive your system to a state that couldn't be reached if you only relied on a single interaction mode. In this video, we are combining different behaviors like pivoting, sliding, and using an external wall to move the object around. So we want to simultaneously regulate both the motion of an object and the interaction of each of the contacts. So in this pair of videos, the controller is trying to keep the palm flush against the side of the rectangle, maintain the orientation of the rectangle, and make sure the object does not slide relative to the hand or ground. So on the left, I rotate the object and break flush contact, and on the right, I move the ground sideways, back and forth. And in both cases, the system is able to regulate the system through these disruptions and recover from them. So this is similar to the previous goal, but we want to close the loop using tactile feedback. So by tactile feedback, I'm specifically referring to a combination of proprioception, so the robot knows the position and orientation of the hand, and wrench feedback, which is provided via a force torque sensor in the wrist of the robot. So here in these videos, the robot is able to maintain the orientation of the object, as shown on the left, maintain the object's position in the world, which is on the right, and in the middle, regulate the relative position between the palm and the object, even as I disrupt it. So I move the system, and then it recovers back to the initial state of the controller. So how are we going to accomplish this? Our plan is to focus on regulating contact behavior. We define a system's contact configuration, which consists of the contact locations of the system, the geometry of those contacts. So in this picture on the left, what you can see is that the palm is flush against the object, so we call that flush contact, and then a corner of the object is touching the surface of the ground, so we call that point line contact. Finally, we'll look at the contact mode, so whether or not a contact is sticking or slipping. So each contact mode in geometry has an associated set of wrench constraints which governs the contact behavior. So here we'll be using the contact configuration as a proxy to regulate the whole system. Oftentimes this is sufficient, but even when it isn't, the contact configuration is a useful abstraction for manipulation. This is a joint estimation and control framework. The estimator predicts the contact configuration using tactile and visual feedback, while the controller tries to impart some desired contact configuration on the system. The two depend on each other. So the controller needs a good estimate of the motion and wrench constraints to efficiently regulate the system. And the estimator relies on the stable motions generated by the controller to explore the different degrees of freedom. So just a quick overview of our, let's go back. So just a quick overview of our manipulation system. It consists of a flat hand or palm, which is attached to a robot arm. We specifically use the Franca Amica Panda. We are manipulating objects in the vertical plane. So that means that gravity is acting in plane. So if the hand departs from the object is going to topple over. We focus on manipulating polygons. Well, in actuality, they're prisms with polygonal faces, but we treat them as polygons. Our environment consists of the ground, which might be offset up or down by some height, and up to 2 vertical walls. And as before, there are 3 sources of feedback. There's proprioception, the robot knows the position and orientation of the hand. The robot is able to measure the forces and torques it exerts on the object using a sensor in its wrist. And then finally, we make use of a limited amount of visual feedback. So I'm going to break up our framework into 3 parts. First, we're going to talk about the model of our system. We'll then develop our estimator. And finally, I'll present how we designed our controller. And after all of that, I'm going to show some demos of our robot doing some cool things. And all throughout, I'm going to be peppering in little bits of related work that are relevant to this thesis. And it's mostly going to be in the estimation and control section. So let's model the system. The goal here is to describe all of these contact interactions using math. Ooh, spooky. So before we do anything, let's list our modeling assumptions. So first, we assume that all motion is quasi-static. So in other words, the system is always at rest. This is very contradictory, right? Like the thing is moving. So it's not actually true, but what we really mean is that we're ignoring accelerations and inertia in the system. So the quasi-static assumption is a reasonable assumption to make when the dissipation in the system is much larger than the inertia. So that means that the system will quickly return to rest after it's been perturbed. We assume that the system is planar. So as such, individual bodies only have 3 degrees of freedom. They can move up or down, side to side, or rotate. As I mentioned before, we focus on manipulating polygons. So, and then the hand, ground, and wall are all represented using straight line segments, with the ground and wall being horizontal and vertical respectively. And then finally, everything is assumed to be rigid. So the hand, object, and environment are not going to deform if we apply forces to them. So our modeling goals is as follows. We start with the contact mode in geometry, which combined we're going to call the discrete contact state. We want to map the discrete contact state to a set of kinematic and wrench constraints, as well as what we'll call admissible motions of the system. So these are the motions that are allowed. To do this, we're going to use a friction model to reason about the contact mode, sticking or slipping. And then we're going to use a geometry model to reason about the contact geometry, so point line versus flush contact. Why are we even doing this? So both our estimator and our controller care about this mapping. The estimator detects the discrete contact state and then uses the corresponding constraints to estimate the shape and pose of the object, while the controller uses the wrench constraints and motion directions to move the object while imparting some desired contact interaction. So during this process, I'll be making use of what we call the generalized friction cone, which is a structure that synthesizes the different wrench constraints of the system. I'm not going to be doing it explicitly, but I would like you to know that this is what's going on under the hood. So for more detailed description of the generalized friction cone, I would point you to Michael Erdman's paper on a representation of friction in configuration space. So we'll now use a friction model to relate the contact mode to a set of kinematic and wrench constraints and admissible motion directions. We use what is called the Coulomb friction law. So a pair of contact surfaces has an associated parameter called the static friction coefficient. This defines a structure called the friction cone, which in these 2 videos is painted in green. So in both videos, what we're doing here is we keep track of the force that the ground exerts on an object. So the force is in dark red, and the object is attached to the robot, which is causing it to move. So on the left, what we see is that as long as the force is on the interior of the friction cone, we get sticking. And then when it's on the boundary of the friction cone, we get sliding, which is the video on the right. So when the red arrow is parallel to the green line, then we get sliding. So in our system, there are 2 contacts that we need to consider. So the hand touching the object and the object touching the ground. Either of these contacts can be sticking or slipping. So let's derive the friction cone for the hand contact. So to do that, we're going to split the force exerted by the hand into components that are perpendicular and parallel to the contact surface, so the normal and tangential components. Using these components, we can draw the friction cone. So that's shown shaded on the right. So on the interior of the friction cone, we get sticking between the object and the hand. And then on either boundary, we get the possibility of sliding. So one boundary corresponds to sliding left, and one boundary corresponds to sliding right. So, but before we move on, I just want to point out the little key at the bottom left of the slide. So we are generating the wrench constraints for the hand contact mode. So if you ever get confused by all of this stuff, just take a look at the key. That's all you really want to know. Everything else is just the low-level details. So you can just take a look at the key. So now we're going to construct the kinematic constraints and admissible motions for the hand contact mode. So during sliding, the hand can move along the surface of the object. And that's just our admissible motion direction, being able to move in the tangential direction. And then during sticking, they can't move tangentially relative to each other. And that's our kinematic constraint. So that's shown on the right. And we just have two different equations for this. You don't need to memorize these or anything. Just know we have one for each. OK, so we've done the hand contact for sticking or slipping. Now let's look at the ground contact for sticking or slipping. So to build the ground friction cone, we're once again going to split the force exerted by the ground on the object into normal and tangential components. So since the ground is horizontal, these are the world horizontal and vertical directions. So like before, the interior corresponds to sticking, and the boundaries correspond to sliding either left or right. But now it's between the object and the ground. Let's construct the kinematic constraints and admissible motions for the ground contact. So during sliding, the object can move to left or the right, as shown in the red arrows, and that's our admissible motion direction. And then during sticking, the contact point of the object on the ground cannot move horizontally, and that's our kinematic constraint. We just have an equation, saying it can't move horizontally. And that's it for our friction model. Let's move on to our geometry model. So as a reminder, our goal is to map the contact geometry at the hand and the ground to a set of kinematic and wrench constraints, as well as a set of admissible motions. So our two possible contact geometries are flush contact and point line contact. So in flush contact, you have two lines that are touching each other. And then in point line contact, you have a corner of one element touching a face of another. So as in the previous set of videos, we're going to keep track of the force exerted by the ground on an object, and that object's attached to the robot, which is causing it to move. And so we're going to compute and plot a point called the center of pressure. And the center of pressure is just this virtual point about which the net resultant torque is 0. And so if we track the center of pressure, which is the red dot shown in the video, what we find is that during flush contact, the COP is on the interior of the contact patch. And then during point line contact, the COP coincides with the contact point. So once again, we need to consider both the hand contact and the ground contact. Either of these can be in point line or flush contact. In our framework, we also consider wall contact, but I'm not going to go into it in this presentation. We don't have the time for that. So for the contact geometry, our wrench constraints can be described using what we call the torque cone, which is analogous to the friction cone. So here, instead of looking at the normal and tangential components of the hand force, we're going to look at the normal component of the hand force and then the resultant torque about the centroid of the hand. And so we can plot basically an identical structure where now, instead of sticking or sliding, the interior corresponds to flush contact, and then the boundary corresponds to pivoting about one of the endpoints of the contact patch. And then the slope of the boundaries of the torque cone depend on the shape of the contact patch. So the hand contact torque cone is illustrated here. There's a couple more layers here, but I'm going to skip that, having to consider whether or not there's overhang between the hand and the object. Just know that I do consider it, but we're not going to go into it. So let's look at the kinematic constraints and admissible motions that are associated with the hand contact geometry. So during point line contact, the hand can rotate about the corner of the object, and that's our admissible motion. And then during flush contact, the orientation of the hand and the object must track each other, right? Because their two faces are stuck together in terms of orientation. And that's our kinematic constraint, which is shown on the right. Also, there's an extra constraint that we have, an extra kinematic constraint. It's called the non-penetration constraint. All this is doing is it's keeping the hand from falling into the object or breaking contact with the object. So we just have one final constraint for that. We're going to skip the wrench constraints for the object ground contact geometry. I do deal with them, but they're a lot harder to visualize and reason about here. So let's just look at the kinematic constraints associated with the object ground contact, as well as admissible motions. So during point line contact, the system, the whole system can sort of pivot about the ground contact point, and that's our admissible motion. And then during flush contact, the object cannot rotate, right? Because it's flush against the ground and the ground's not rotating. And that's our kinematic constraint. And then finally, we have the non-penetration constraint, which is, keeps the object from falling into the ground or breaking contact from the ground. And that's our model. So let's summarize it. So we start with a discrete contact state, which consists of the contact mode and contact geometry. And then this is then mapped to a set of kinematic and wrench constraints and admissible motions. And we're going to use this for our estimator and our controller. And so just all the equations listed up here, you can forget them forever. So it's Morgan time. I mean, it's estimation time. Let's look at our estimator. The process is as follows. We start with tactile and visual feedback. And then with this, we're going to estimate the contact mode and geometry using the friction module and the geometry module, respectively. Once the estimator has predicted the discrete contact state, we're going to assemble the corresponding kinematic constraints, which we just described in our model. And then we're going to synthesize them into what we call a factor graph, which is just a constraint satisfaction problem whose solution is going to be the estimate of the object that we're manipulating, the shape and the pose. And then the result of the estimator is going to be fed into the controller. So let's start with the friction estimator. Here's a video of the friction estimator in action. So as the robot moves the object around, it estimates the friction constraints, which are shown in green. Those are the estimated friction constraints. And then these constraints are then used to estimate whether or not a given contact is sticking or slipping. So before I get into the details, I'd like to touch on the work that was done by Jiaji Zhu. He designed a framework for estimating a structure that we call the limit surface, which relates contact forces to motions. And to do this, he generated data by having a robot push an object around on a table and observing how it moved in response. The friction cone and the limit surface are very related structures. However, the limit surface isn't really useful for this specific problem. The main issue is that in my system, there's a rotational degree of freedom that's present even when both contacts are sticking. So not really applicable for us, but very adjacent research. So the way the friction estimator works, it's in two steps. First, we're going to estimate the friction constraints. So in the ideal case, any measured force is going to be on the interior or the boundary of the true friction cone. So all we need to do is find the set of constraints that contains all the measured forces. So for the hand contact, what we do is we essentially find the smallest cone centered at the origin that contains all the measured hand forces. The ground contact involves something that's a little bit different. We generate something called the convex hull, which you can think of it as just the smallest polygon that contains all the measured points. So once the constraints have been approximated, we can compare them to the measured force. So if the measured force is on the interior, we get sticking. And then if it's on the boundary, one of the left or right boundary, we get sliding either left or right. There's a lot more detail as to how this works, but our time is limited. So we're going to move on. So let's look at our geometry module, which predicts the contact geometry using feedback and then also the previous estimate of our system. So here's the contact geometry estimator in action. The active vertices, active contact vertices and edges are shown in red. So before I get into how we implement it, I'd like to talk about the work done by Shuai Li. Li's framework estimates the contact geometry using what we call particle filters, which is a very popular nonlinear estimation framework. The biggest difference between our works is that one, I don't use particle filters in my implementation, and two, we also estimate the object shape and the environmental parameters as part of our estimation loop, which is not something that they do. So instead of particle filters, we just use heuristics, so rules of thumb for our geometry estimator. It would take too long to go through every single heuristic, so I'm just going to give one example, which is predicting the contact geometry between the object and the ground. So there are three cases here. In the first case, if the estimated vertex position of the object is like way below the rest of them, then that's probably the one that's in contact with the ground. If there are two vertices that are around the same height, you probably don't want to rely on the shape and pose estimator to find which of the two are in contact. So what we instead do is we're going to look at the center of pressure. So if you remember, right, during point line contact, the center of pressure coincides with the contact vertex. So if the center of pressure is close to one of the estimated vertex positions, that's probably the one that's in contact with the ground. And if it's in between the two, that's when we get flush contact. So now that we've estimated the mode and geometry of the hand and ground contacts, we're going to generate the set of corresponding kinematic constraints. And then we're going to synthesize them into a factor graph whose solution is going to be an estimate of the shape and pose of the object we're manipulating. So here's the estimator in action. It's able to keep track of the shape and the pose of the object as we go through a sequence of interaction modes. Before I continue, I'd like to briefly discuss the work done by Sudarshan Suresh, also known as Sudo, on this problem. He uses factor graphs to synthesize kinematic constraints to simultaneously estimate an object shape and pose, just like we do. But he's also able to reason about shapes with curves like circles or ellipses. We only deal with polygons. However, his framework only reasons about contacts that can be directly observed. So in our framework, we do deal with the ground contact, which you don't observe it directly. It's called it's an extrinsic contact. You have to measure it indirectly through the hand contact and infer that behavior through the hand contact. You don't know its position, like you have to infer it from the motion of the system. Since the object is assumed to be a polygon, we're going to represent its shape using the position of the polygon vertices in the object frame. We also keep track of its pose, which is just the combination of position and orientation in the world frame. And then finally, we also estimate the height of the ground. So we are able to measure the pose of the hand through proprioception and the wrench exerted by the hand on the object through the force torque sensor in the wrist. And then we use vision to give us a noisy estimate of the object vertex positions in the world frame. And vision is just primarily used to generate an initial guess to warm start the estimation loop. We usually don't use it online. And as a reminder, we're trying to estimate the shape and pose of the object. So to do this, we're going to assemble the active kinematic constraints from the estimated contact mode and geometry for both the hand and the ground contacts. And we're going to use the same exact mapping that we described in our model. So we then synthesize these constraints into using a factor graph. So what is a factor graph? Well, first, it's a type of graph, which just is a set of vertices and edges that are connected to one another. And so for a factor graph, each vertex represents either a variable or a constraint on a variable. And then the edges relate variables to constraints. Factor graphs are a popular tool in the estimation community, and they're used to represent constraint satisfaction problems whose solution is an estimate of the system's parameters and pose. We use them mainly because there exist a lot of great software toolboxes that already exist to quickly solve factor graphs and generate an estimate. We specifically use a toolbox called GTSAM. And so here, in the context of our problem, the constraint vertices correspond to the kinematic constraints listed in our model, and the variable vertices corresponds to the shape and pose of the object. And then we solve the factor graph to generate our estimate. And that's our estimator in its entirety. Let's move on to the controller. So as I mentioned at the start of the talk, manipulation systems are usually hybrid, which presents a significant challenge for estimation and control. So one great example of planning and control through multiple interaction modes is the work done by Zach Woodruff and Kevin Lynch. Kevin Lynch is on my committee, and he's here today. They developed a framework for planning individual motion primitives and then scheduling the primitives to drive the object to the desired pose. One of the big differences between their work and ours is that we have not written a scheduler to sequence the motion primitives, but we do have an estimator to predict the object's shape and pose, which they do not. Also, their system is dynamic while ours is quasi-static. Also, our controller is focused on simultaneously regulating the pose and contact interactions of an object. So Yuki Shirai has also worked on a framework for this kind of problem. His team makes use of GelSight, which is a high fidelity contact sensor. And they also interact with the object through a tool that is being gripped by the robot. So we don't do either of these things. However, our robot is able to intentionally drive the system to slide at both the hand and the ground contacts, whereas they always just maintain sticking. So in our control framework, we start with me. I'm sending high-level motion commands in the form of motion primitives to the system just through a keyboard interface. These are received by the contact configuration controller, which converts the primitive command and information generated by the estimator into a target pose of the robot hand. The target pose is then passed to an impedance layer, which executes the motion on the robot. So we're going to go in reverse order here and start with the impedance layer. So impedance control, it emulates a spring, but not really, a mass spring damper system. So, but for the level of granularity that we're going to go into in this presentation, you can just think of it as a spring. What we do in impedance control is we specify a impedance pose target, which is the pose of the hand that the robot is trying to get to. The robot then exerts a wrench. So a wrench is a combination of a force and a torque to drive the hand towards the target pose. And this wrench is proportional to how far away the current pose is from the target pose. The proportionality constant relating the pose error to the corrective wrench is called the stiffness of the system. And we have a translational stiffness, which here is denoted as Kf, and then a rotational stiffness, which is denoted as K theta. So impedance control is useful for our application for two reasons. First, it inherently provides a degree of compliance that we're looking for to be robust to estimation error. And then second, it provides a natural interface for simultaneously regulating wrenches and poses. So let's get into that second statement a little bit. So impedance control can be used to regulate the wrench exerted by the hand. So in these videos, the impedance target, which is shown in pink, we're moving it around, up and down, sideways, rotating it. And as you can see, and at the same time, right, the hand is constrained to be stationary. And so as you can see, as we change the impedance target location, the force exerted by the hand, which is shown in blue, or the total wrench, changes to follow it, essentially. So for the figure on the right, the center of pressure location, which is shown as a red dot, is sort of the proxy to describe how the torque exerted by the hand is changing as the impedance target rotates. So impedance control can also be used to regulate the pose of the end effector. So in the videos above, as we move this pink impedance target around, the hand follows it because there's nothing to keep it from reaching that pose. And that's impedance control. So the question now becomes, how do we choose the impedance pose target at every time step? And so we do this with our contact configuration controller. So in designing our controller, we need a balance between two regulation objectives. We need to regulate the contact wrench so that it satisfies the wrench constraints of the contact mode and the wrench constraints of the contact geometry for whatever motion primitive that we want to execute. Then we also want to regulate the pose of the hand in such a way that it moves the object in the way that we want to. So two different objectives, one wrench objective, one pose objective. And we need to do both simultaneously. This isn't like a new problem. One very popular approach to simultaneous wrench and pose regulation is through what we call hybrid force velocity control, or HFVC. So in HFVC, you sort of partition your space into perpendicular directions, and you sort of select a subset to be your force control directions and another subset to be your velocity control directions. And what this does is it splits your control problem into two independent problems that can be solved separately. And so you have a force controller for one and a velocity controller for the other. So this was a method that was used in the work done by Yifan Ho and also the work done by Jackie Liang for a system that's very similar to our own. HFVC is great for robots that don't have an impedance control interface. However, I would argue that the controller I'm about to present allows for dynamic balancing between control objectives, and it doesn't require accurate knowledge of the admissible motion directions of the system to function properly. In addition to this, the framework that I'm going to show you allows for very reactive closed-loop behaviors. So this is our contact configuration controller. So it takes the commanded motion primitive, the estimated wrench constraints, and the estimated admissible motion directions, and it converts them into an optimization problem, specifically a quadratic program. And the output, the solution to this quadratic program, is where to place the impedance target at the next time step. So here, the optimization cost is used to drive the robot hand along to encourage the robot hand to move along the desired motion direction. The constraints correspond to the wrench constraints that we already described in our model to enforce the right contact geometry or contact mode. So the pose target and the wrench are related via the impedance law that we just described, and that this is an equality constraint in our contact configuration controller. Here are some videos of the controller in action. The impedance target is shown in orange. The estimated friction constraints are shown in green. And then the commanded motion for the whatever primitive is shown as the red arrow. Then the red regions that are painted in correspond to the actual optimization constraints in the quadratic program. And so when a contact is sticking, when you want to enforce sticking, then the optimization constraints are just identical to the friction constraints. And so you end up with a red triangle aligning with the two green lines. However, when we command sliding, we're going to ignore the portion of the friction cone that is preventing sliding in that direction. And so that expands our constraint region into the trapezoid. So that's what you see in the middle video and on the video on the right. So in the middle video, if you look at the hand contact, you get the trapezoid. And on the right video, if you look at the ground contact for ground sliding, you get another trapezoid. So here's another visualization of our optimization problem. In this case, the controller is trying to rotate the object about the ground pivot. The friction and torque constraints are shown separately in the middle. And then when you combine them, these constraints form the three-dimensional structure shown on the right. And that's actually just the generalized friction cone that's what I talked about at the very beginning. And so the admissible motion direction for rotation is denoted as that, like in the figure on the right, the little arrow that's emanating from the orange region. Okay, so these pair of videos here demonstrate that we need the contact configuration controller. The impedance layer by itself is not going to cut it. So on the left, the impedance layer is operating by itself, and it's failing to regulate sticking contact or the angle of the triangle. And then on the right, we have the contact configuration and the impedance layer working together. And it is able to actually regulate both the orientation of the object and then the contact behavior at both contacts. Okay, so here's a question. How do we choose the stiffness of the impedance layer? Well, the answer is we go all Goldilocks on it. So if the stiffness is too low, then what we get is that the system is going to oscillate as the controller plays a game of catch up with the system dynamics. And so that's the video that you see on the left, some oscillations. Then at higher stiffnesses, the motion is much more steady. So that's the video on the right. That being said, if the stiffness itself is too high, the impedance controller becomes unstable. So on the video on the left, the robot is able to track a circular path while in impedance mode. And then on the video on the right, the stiffness has been set way too high, and the robot just freaks out. So as long as the stiffness is not at one of the two extremes, the controller usually works pretty well. So the contact configuration controller takes in high-level motion commands as input, and currently I'm the one that sends the commands via keyboard interface, but if I had more time, I would have written a high-level planner to do it for me. However, I've still sort of partitioned the problems of planning and control. So usually planners would have to reason about the different contact interactions at every single time step, but here you sort of have individual behaviors, and then you can have a mode scheduler that just sequences them. We have many primitives, but the three main ones are, so you have first on the left, pivoting the object about the ground contact. In the middle, we can slide the object along the ground. And then finally on the right, we can perform a regrasp where the hand slides along the top of the object. And that's our manipulation framework. Pretty cool, right? Let's look at some demos. So I already showed you this one before at the beginning, but let's take a look at it again. Here, the controller is able to reactively regulate the pose of the object using tactile feedback. So I'm rotating it in the left video, and it's still able to recover. In the middle, I'm sort of displacing the relative pose between the hand and the object, and it's still able to recover. And then on the right, I'm translating the whole thing, and it's able to return to the initial position, all while regulating the desired contact behavior. The controller can also enforce flush contact between the hand and the object, even when there's a bit of overhang at the hand object contact location. So that's the video shown on the left. So there's a little bit that the hand sort of overhangs the object. And so this is only really possible because we're keeping track of the object vertex locations in the world frame using the estimator. Otherwise, the controller could accidentally go into point line contact. So we also have developed a set of motion primitives where the object is in point line contact with both the hand and the ground. In this interaction mode, we can either rotate the entire system about the ground contact, or we can just rotate the hand about the object contact. So that's a video shown on the right where the middle one is rotating the whole system about the ground contact. We can also manipulate the object while it is in contact with the wall. So on the left, the robot is rotating the object, and on the right is performing a regrasp by sliding the hand along the object. And then finally, if motion primitives are sequenced together properly, we can drive the object from some initial state to some desired state. And this is the demo that I showed you before. So exploiting hybridness. So I'd like to conclude this presentation with some final thoughts. So first, a big theme of this work is contact configuration regulation. It's in the title of my thesis. I do think that our results demonstrate that regulating contact behavior is an effective approach to manipulation. Second, I'd like to point out how similar the structures of our estimator and controller are. So as a reminder, we start off with the discrete contact state, the combination of the contact mode and geometry, which in the estimator we estimate, or in the controller we're trying to command. And then this maps to a set of kinematic and wrench constraints and admissible motions for both of them. We then synthesize them into an optimization problem. So for the estimator, that's a factor graph. For the controller, that's a quadratic program. And then the output is either the estimate of the shape and pose of the system for the estimator, or the impedance target pose, which we use to regulate both the pose and the contact behavior for the controller. Finally, I'd like to give a shout out to the impedance control layer, which allows the controller to work so well. The impedance layer bakes in, as I said before, a level of compliance that is forgiving to estimation error, and it provides a natural interface for simultaneous wrench and motion regulation. And that's it. Let's move on to acknowledgments. First, I'd like to thank my advisor, Alberto Rodriguez. I've had the pleasure of working with Alberto ever since he invited me to join his lab 9 years ago. Thank you for taking a chance on me, Alberto. Thank you for helping me grow as a researcher and giving me the freedom to explore how I wanted to. I had tons of fun, and I hope you did as well. Next, I would like to thank the rest of my thesis committee, Professor Triantafylos Achilles, Professor Neville Hogan, and Professor Kevin Lynch. They gave me a ton of great advice as I worked towards completing my thesis. Also, I should mention that I TA'd dynamics for Professor Achilles for 3 different semesters, and that was a lot of fun. I would really like to thank my good friend, my collaborator, and in some senses, my other advisor, Neil Doshi. Everything that I just presented now was developed jointly by the two of us, and I'm really grateful that I had the chance to work with you, Neil. I'd also really like to thank my lab mate, Rachel Holliday. Rachel spent an unspeakable amount of time setting up the robot that you just saw in all the videos that we use in our research. This project would not have happened if it weren't for her efforts. I'd also like to thank Sudarshan Suresh, also known as Sudo, for all the advice he gave me as I worked on the second iteration of our estimation framework, which is the estimator I presented today. I would like to thank my lab. I've been at the MCube lab for 9 years as a graduate student, and I've got to meet many amazing people during those 9 years. Thank you for making my time at the lab so enjoyable. I would like to thank all of my undergraduate professors at the Olin College of Engineering. I'm really appreciative of the fundamental foundations in math and engineering that they helped me develop over those 4 years. I'd also like to thank all of my middle and high school teachers. Just in general, I love all of my mentors, all of my teachers, and all of my professors. Thank you. I'd like to thank all of my friends, my pals, for their support and friendship all of these years. And last but not least, I would like to thank my family who are here in the audience today. I'd like to thank my parents, Kevin and Ruth, my siblings, Ileana and Ian, and my partner, Maya. Thank you for all of your love and support as I went on this journey. So thank you. And that's that. Let's open the floor to questions.
Excellent. Who wants to go with the first question?
Thanks for that. That was a very cool presentation.
Thank you.
So when you're doing the shape estimation, you're using vision to kind of warm start with where the vertices are, and the factor graph optimizes the placement of those vertices. A priori, do you ever know the number of vertices, or is that does the vision module know that?
Okay, that's a good question. So the vision module, the way it's constructed, it tries to infer it, and usually because the object is a polygon, it actually is able to pluck out like those vertex locations. There's a whole thing. I've made this convex hole estimation module that sort of approximates. So if you have a bunch of data points sampled from a polygon that's like with noise added to them, it's able to actually reconstruct what the initial generating polygon was. And I use that as part of it's both for the friction estimator and then also for the vision estimator. It's just a heuristic, nothing like super research going on there, but like it's able to actually generate the number of vertices.
Cool, thanks.
Orion, I'm so glad to see you at this point. So I just wanted to start by saying this is a great presentation, and I'm really, really happy to see that you're here now.
Thank you.
Question I have you, I guess, actual technical thing. That's my excuse for getting to say that. When it comes to estimation of the friction cone, I think in the slide that you showed, you had mentioned like the voiceover, you talked about finding the minimum cone, but it looked like the boundaries that you drew actually ignored a handful of points. I'm wondering, is there some kind of like noise rejection that you're doing in there?
Yeah. So in the hand friction cone, what I essentially do is there's a layer that's a sort of a unidirectional low pass filter. So it sort of allows for expansion of the angles of the cone, but like you have to get points outside of it, and it sort of each point will pull the cone boundary towards it. And there are a couple of like little magic things that I did where like there's a maximum sort of step that it can grow, and then but then there's also a proportionality constant if it's less than the maximum. And so in actuality, right, like the big thing is that you don't want to just like, say you go over a crack or something and you feel a jolt. You don't want that to suddenly disrupt the friction cone permanently. So there's a bunch of noise reduction to keep that from happening on several different layers.
Cool. Some more Orion heuristics.
Yep.
Any more questions?
Yeah, we have a question from Neil online.
Oh.
Hey, Orion. Can you hear me?
How's it going?
Good. Nice job. That was an awesome
Thank you.
presentation. I have a question. It's more meant to be like an open-ended thing for you to like kind of share your thoughts. But the workhorse in this project is sort of using mechanics to define these constraints for wrenches and motions. What would you do if you did it again? If the mechanics were a lot harder, say the surfaces were curved or things like this, or if like the mechanics were well defined, say for something that was soft or a little bit compliant. How would you like go about trying to solve those problems? And like, no wrong answer, just kind of want to hear your thoughts.
So I think there's just a fundamental limitation on model-driven approaches. Like I made so many simplifying assumptions, and every time that I've tried to remove a simplifying assumption, even like the easiest one to remove, like the object being curved, everything sort of breaks. I really think that a learning-driven approach is probably preferable at some level. Perhaps you can still make use of a model-driven approach for like, you can have a separate module here that you reason about like very basic interactions. But once the system reaches a certain level of complexity, I really think just using some kind of machine learning model to either estimate the friction behavior or generate some kind of controller. I think there's a lot of utility there for learning. But once again, I'm not a learning guy, but there are a lot of learning people in my lab, and it seems as though, right, they're able to deal with far more complex things than I can in terms of the system description itself. I'm not saying that this work isn't complex. It's just there's a certain axis of complexity that I'm going down that I'm not able to really explore other axes just because I made the choice to go model-based.
Yeah, thank you. That's like, yeah, it's a great answer.
Any other questions?
Very impressive, Orion. I've got an unfair question. Suppose we were to require you to do this now with objects, polygonal objects, but in 6 dimensions rather than 3. What would be the main bottleneck?
So, you mean with 6? Okay, so in the real world, yeah. So I've thought about this a lot because, I mean, for instance, Ifan's work, 3D. I think it's sort of broken down into 2 parts, because the question is, how do you want, like, what level of 3-dimensional motion do you actually want to realize? So for instance, you could try to say for regulating this bottle, right? You could have like a separate controller regulating this way or a separate controller regulating that way, and just use the 2D controllers. But that's not really a satisfying answer. Like ideally, you want to be able to drive the object in the full space. And so for the first thing, for instance, is that the friction cone construction that I have is not going to cut it, right? You really would need to actually reason about the limit surface, because you have this patch contact that has all these different motions. So whatever model you construct, it can't just use the basic friction cone estimate. However, I think the actual control framework is, in some ways, could be ported, right? Like you have the different admissible motion directions. I think that could be directly ported over from 2D into 3D. If you're using, a different structure than the actual wrench constraints, then that's not going to necessarily be ported over into the constraints of the QP. But there might be a different optimization program that you could write to still try to satisfy those constraints in the contact node. So I think just at the very least, the general idea of having like wrench constraints to enforce modes, and then also reason about the directions that you want to drive the system in, and then synthesizing them together using some type of optimization. I think that general concept holds, but I think that you're going to be very sad if you try to directly port this system into 3D. It's not going to be very satisfying.
I have a question. Can you go back to your slide where you have the final discussion points? Yes, final thoughts. So presented 3 parts, right? So modeling, estimation, and control. The modeling is 1, right? So the mechanics of the system, whether you use them for estimation or you use them for control, they're one sort of like combined perspective that ends up in sort of kinematic constraints and range constraints. And now you sort of presented how both the estimator and the controller have their own way of doing the math, right?
Yes.
And sort of combining them, choosing them, which ones. But in one case, you use a factor graph. In the other case, you use a quadratic program to do that sort of amalgamation of constraints. Do you have a sense as to what is the reason for that? Or if there could be some more sort of general approach to solve both?
Yeah, so first things first, I mean, I feel like the factor graph formulation is not something that's necessarily set in stone. I think the main reason that we use it is because of the toolbox that exists and because of the fact that it's so popular in the estimation community that it provides a natural blueprint for framing these kind of problems, as you all know. The quadratic program just happens to be something of my own design. I don't even think that like you need specifically a quadratic program. It's just that it was an optimization program where you could sort of frame the right kind of costs, and there exist solvers to very rapidly solve problems of that structure. I think that you could conceivably find a sort of a more unifying problem that you could solve. Like, for instance, you might be able to port the factor graph over into the controller itself, right? Sang-Woon did that, as well as Yuki, I think, also did that. I don't think the quadratic program necessarily would port over to the factor graph, but the important thing, right, of the factor graph is it's just a constraint satisfaction problem. I'm just framing it that way, where the system is over constrained, so you don't want to frame it as an exact constraint satisfaction problem. You want to frame it as some kind of optimization, but it doesn't have to be a factor graph. Like any sort of thing where it's like you impose constraints and the thing that satisfies those constraints is the answer, I think would work. I don't know if that addressed your question.
Yeah, cool. Thanks. So we have a question from Kevin online.
Yes.
Yeah, thanks for that presentation, Orion. That was great. As always, the experimental demonstrations are really impressive and sometimes surprising. Like you show some manipulations that I think maybe shouldn't be possible, or I don't really understand why they're possible. And then there's several places in the thesis where I think speaking to Alberto's comment about your authenticity, you're very forthright in saying, I'm not exactly sure why this works the way it does, but it seems to work well. And you mentioned just now, there's some magic going on with your reduction of your estimation of the friction. So I want to push on that magic a little bit. So two questions. One, Alberto was just referring to it. So you have this very sort of mechanics-based way of thinking about manipulation modes. You have rigid contact that give you kinematic constraints. You have Coulomb friction, which is a really nonlinear, there's really no softness or smoothness to the model at all. And then you've got this very soft quadratic program combined with this magical, Franca controller that does impedance control. And then somehow you get, at the end, you get these kind of beautiful motions out of it. And I just wanted to pick at that a little bit because it seems like, this sort of very nonlinear modeling that you're doing kind of gets smoothed out in this weighted optimization that allows you to violate the constraints that you spent some time developing. But maybe as a result, it works. So if you choose the right feedback control parameters, et cetera, for the Franca, which is another piece of magic that I assume comes from experience. So I just wanted to hear you comment a little bit on how you think, whether it's important that you have this sort of non-smooth or this smoothing optimization that goes with your non-smooth model and why that works together. Why should it work at all? And so that's my first question. And the second question is, some of these manipulation modes do seem surprising, like, oh, you're able to slide the hand while it's in point, the object is in point contact. And I wonder if there are any manipulation modes that you have proven through your model are impossible to do. Like, so if you had asked your robot to do it, it shouldn't be able to do it. Or it depends on the friction coefficients. Or, or if everything that you have shown, you've proven sort of analytically can be done. So that's sort of the second part of it, just with the strict model.
Okay, so let's address that first question. So I'd like to start out. I had a discussion with Alberto, a couple months ago, maybe like a month ago, about how he suggested that the controller is the contact configuration controller is, in a sense, like a promise that you make, that you sort of a handshake agreement that you make with the world. Like, none of those constraints necessarily, there's no guarantee that any of them should apply. And yet, through the fact that you have this reactive closed loop controller and you're trying to impose that on the world, it somehow is realized. I think a big part of this is how closed loop the controller is. Like, we spent a massive amount of time when we went through so many different iterations of the controller. We really initially were very much on sort of the feed forward philosophy. Like, let's predict how moving the impedance target is going to adjust the pose of the system, both like how it's going to cause the object to rotate and how it's going to cause the hand to slide. And there were many failures associated with this. Two main reasons. One, the actual underlying impedance controller doesn't, like, it's only approximately true, like moving the pose up or down is going to, like, it'll moving the target up and down will cause the force to move up and down, but it's not actually going to be doing it by that stiffness constant. And then the second thing is that it's tough to come up with a feed forward model where, you have this, usually in planar pushing, right, every degree of freedom is constrained by friction. There's some frictional resistance, but for our system, we have this rotation and then also the sliding. And that just threw a wrench into any sort of analytical approach to sort of predicting what the future was. So our solution ended up being this closed loop controller, right? So at every time step, it's trying to enforce the contact mode, enforce the orientation. There's no guarantee that, for instance, for different axes of the controller or different sort of regulation objectives, it's sort of assuming that the other ones are already correct. So like in trying to regulate sticking, it's doing so sort of under the assumption that the orientation is correct. And the same, like vice versa. And neither of those are necessarily correct, but the closed loop nature of the controller is able to actively, I guess, get the conditions that you need for the regulation to actually be effective. I think that's what I mean to say. So parts of the closed loop nature of the controller drives the system to a state where the regulation, where the parameters of the system are in a way that you're able to actually regulate it in the way that you want. And then the other thing, right, is that even though it's discontinuous, like, I guess the best way to say this is that, for instance, when you're regulating sliding, well, we're not actively considering the friction cone when we try to regulate like force sliding in a certain direction. All we're doing is moving the impedance target until it's slid by that amount. And it's usually unidirectional. So if it does pass the target location, then it'll just terminate, and that'll be that. There will be some error, but that's all it's doing. So even though like you have these discontinuities in the model, and I guess also in the dynamics, because you have like a high stiffness, which means that you can move the pose a little bit, and it'll just move a little bit until you get it to where you want. The controller ends up working. And then on the second point, as to proving whether or not something is, analytically yay or nay, first thing I'd like to say, friction coefficient, object geometry, very important onto what behaviors you can actually do. All of these videos have, like, I've chosen the friction coefficients in a way that these behaviors can all be realized simultaneously. For instance, if you have just a block sitting on the ground, and you have the friction coefficient on the top and the friction coefficient on the bottom, depending on their choice, it's often only possible to either slide on the top or slide on the bottom. It depends on the weight of the block and the two friction coefficients. There's only like a very special region where you can actually do all three. We do have visualizations of the quadratic program, which show how the various wrench constraints are currently aligning at any given time. And when you look at that, oftentimes, I mean, it's not saying that something's not analytically possible, but once there's no feasible region in any of the wrench constraints, the controller is just going to stop. And that's how it works. But that doesn't, I don't think that necessarily means that a motion is or isn't possible. You know, fundamentally, because we didn't rely on any forward model, I'm unwilling to make any predictions about whether or not something is fundamentally possible. I can just say whether or not the robot can do it. And that's as best as I can give, unfortunately. I don't know if that answers your question.
It's in that direction.
Okay, sorry.
No, that's good. Thanks.
Didn't mean to ramble, but.
Any more questions? Or we want to close the door? All right. So one more thanks to Orion and